Hello, quantum explorers.
I'm curious qubits.
Oh, very cool. Welcome to our first episode of The Quantum Kid.
That's me, I'm Kai. And what even is a qubit?
That's a very good question. What is a qubit? We'll find out. That's exactly what the show is going to be about. We are trying to demystify quantum for quantum leaders of today and tomorrow. Today we have, for our first episode, really great guests joining us. So the first one, do you remember who it is, Kai?
Renato?
Renato. It's a ETH Zurich professor, Renato Renner. Welcome, Renato.
Hi, I'm a professor at ETH Zurich and we do research on quantum. We try to use it for everything and in particular we try to understand what it is.
Actually, the question you had, right?
Yes, so what even is quantum? And what I said before, what is a qubit?
These are good questions. And quantum mechanics is 100 years old and people are still fighting and debating about what it is. It's about physics of very small things. So you can imagine when you maybe have used Google Map in the past, then you can zoom in. And imagine now that you can zoom in much more. You can zoom in to one, let's say, house and then to the table and then what on the, let's say, there's an apple on the table. You zoom into that, then you zoom into the skin more and more. Then you see at some point atoms, and the atoms are small things. We can still imagine they're like little balls. But then when you zoom in even more, you see that things are very different from what you're used to. They move differently, they behave differently, and they're just completely different. It's like as you open the door to a new world where there are very different laws. Nothing is as you're used to. For example, if you think that in our world a ball is in a certain place, you can go there and see it. This is no longer true in the quantum world. So a ball can be at several positions and you cannot go there and grab it. It's just spread out somewhere.
How is that possible? That it can be in different places at the same time? Well, one object being in 1 million places at the same time.
The problem is that we have a language where we say something is in different places at the same time. But actually, as soon as you go there and check, it will be again in one place. People say it collapses to one place. If you don't look where it is, it will be spread out again. So we don't even have, let's say, the language to talk about that. It's neither in the different places, but it's also not in one place. It's something very different. And because our whole way of thinking when we grow up, we get used to things. We get used to things that we can see, but because this world is so different, we are not even used to talk about it. So any description that we are giving, like it's now at the same time in these places, is not valid. Now you were asking, how is this possible? Actually, when you're born and look at the world, you could ask the same question about everything. How is it possible that things fall down onto Earth? How does a ball know what is down and what is up? He doesn't have any eyes to see that the Earth is downstairs and the sky is upstairs, but still it falls in one direction. It's just, these are the laws of physics. Now, if you go to the small, there are new things that we find very strange, but they're still just the laws of physics. And the only thing we can do is to check what's going on and then describe it and just accept that it is like that. And in physics, we cannot answer the question why. We can just observe it and describe it. And so the quantum world is a different world and we should just enjoy exploring it and try to use it for something useful. That's then the second step.
Yeah, that's exactly why we wanted to explain quantum computing specifically. So how can we harness, the powers of nature in this case? How can we mimic nature to make something useful out of it?
Now we said that a particle can be at different places at the same time. But now you can imagine you have a computer. A normal computer takes one input. For example, if you have a little calculator, you can give it the calculation like calculate 3 times 5. Then it will do it. But it will just do this calculation. Now in a quantum computer, you can give a number which is not one number, but many numbers at the same time. Instead of 3 times 5, you calculate at the same time 3 times 5, 7 times 5, 9 times 5, 11 times 5. These are all calculations that are happening at the same time. It's not the usual way of happening at the same time. We cannot see all the results. We have to be very clever to make use of that. But somehow it's doing things in a way which we could never imagine if you just give one number. It calculates with all the numbers simultaneously. The problem is that we cannot read this out. So we need to be very clever to make use of that. And for that, we need software engineers, people who study quantum computers. And we don't have many of them because quantum computers didn't exist in the past. So now maybe when you grow up, you have the chance to study quantum computing, and then you will maybe be one of the first persons who know how to use these machines, because now we know still very little. We are just building the machines and no one knows precisely how to program them. We have very few programs. We can do a few things, but I think most things that we will be able to do have still to be invented by you, actually.
Very cool. And you had a question before. We were talking about airplanes, right? So like just if we could mention specifically the uses of quantum computers now that they are still being built and they're getting more and more mature. Very soon we will have this technology within, according to some companies, within the next 5 years or so, we may already achieve what they call quantum advantage. So when a quantum computer will be better in certain tasks than a classical computer. But what's the use of it? And Kai, I think you had a very good example, right?
Yeah, I'm trying to make a DIY model airplane, remotely controlled. And how could a quantum computer in the future help me with that airplane?
Yeah, that's a good question. And imagine you have not only one airplane, but you have many airplanes and they're all flying around and you want to make sure they don't collide. Of course, you want that. Now, in a normal airplane, you can maybe say if an airplane sees the other one goes up and the other goes down, so they can cross each other. But now it's a problem because if one airplane sees another one, they have to decide which one goes up and which one down. So they have to somehow agree who does what, and they have to be very fast in doing that. Now, this is very difficult for a computer because if you program a computer, for example, you say, if you see another airplane, then go up. But then if that airplane meets another airplane that has the same computer, that airplane will also go up. Then they will both go up and still collide, which is bad. Now, a quantum computer, actually, this is something we even proposed in our research, could be used to make sure that two airplanes that meet always do the opposite thing. So whenever they meet, one goes up, the other down, and then they can cross without harm. So that's one application, which is just to make sure there are no airplane accidents if there are too many airplanes around it. So you can have many remote-controlled airplanes and they will all fly around without crashing.
Well, when there's bad weather and there's like wind coming from like north and your plane needs to go north, how could a quantum computer help so it maneuvers through the air and knows where the wind's coming from and it can know where to go so it does not go very slow?
So they're very good questions, but we need many people in the future who think about them very deeply. And I think that's a good thing. If everything was already known, it would be a boring world. So you will grow up with a new machine that can potentially do new things, and you have to think about how to use it. And if you were born, let's say, 100 years earlier, then the computers we are now using were at the same stage as quantum computers now. They were very slow. We had almost no programs. And if you had asked at that time, how do we use a computer to communicate now, to talk to each other over the web? No one would have had an answer at that time. Because we had so many clever people in the last century that developed all that software, we can now do it. But now we are exactly at the same stage. So we need many clever people so that in maybe 50 years later, we can do all that. For example, control the airplane in a clever way.
Oh, very cool. Actually, I'm thinking that this is a really good segue to talk a little bit deeper about optimization, because the example you were describing is effectively how to optimize this air travel, right? And that could be applied to so many different things, including shipping and logistics on the ground as well as in the air or on the water. And our second guest today deals exactly with that. So, and by the way, Kai, that is going to be your super cool uncle, Andrei.
Yay!
Andrei, thank you for joining us.
Thank you for inviting me. I'm a patent attorney, so I specialize in all new inventions and new technologies, and I really enjoy it. I'm an engineer by training, but in the past 10 years, I've been also an investor. One of the companies we have, it's a logistics company that has several trucks, and we also have a system. We provide a service to other companies that have trucks that drive around the different regions to deliver goods. Another company we have has to do with sailing. But what I do is I also often look for startups or for technologies where I can potentially invest as a patent attorney. That's will be later able to license those technologies to the industry to scale them. And of course, quantum computing is something we've been discussing, and it's the next big thing for us in the IP world, because originally we had AI and now we have quantum, and everybody's asking, is it going to be mature enough to make money, to be actually applicable to real businesses? And this is what I'd love to ask. What do you think? When can we count on that? And how should we even look at it? Because I don't understand most of it.
That's great. I mean, you just described several problems, I guess. So maybe if we just start with logistics and shipping, because that's similar to what you were asking about the plane. Sakai?
Yeah, so what I want to do in my airplane is that it would build it first, program it with Python, and it will be using a GPS to fly to a location it needs to go to. Then it will drop off the mail that I want to give to my friend or something. Parachute will deploy, and then it will be going down to the person who I want to give it to. And that's why I asked the question before about how could a quantum computer help when the wind's coming in the direction it needs to go.
To optimize the best flight path and also optimize the best shipping route. So I guess, Renato, lots of questions for you here.
Yes. So what is called optimization is to find a good solution among many possible things. So actually, when you walk from one place to the other, you try to find the shortest path. And sometimes it's difficult to find the shortest path. You need to write down all of them and then see how long they are. Now, in physics, this optimization often happens automatically. For example, if you make little bubbles with soap, they are perfectly round. And the reason they are round is that this is the best shape you could imagine, where the surface is very small, but still the volume is large. So in a sense, the bubble searches for the best shape to minimize the amount of soap it needs, because that's how large the skin is or the surface, but it still wants to be big. There are many such things happening in physics, and even more in quantum physics. And now what you need to do is to somehow translate the problem that is useful for you, for example, flying airplanes efficiently. You need to map this or translate this to such a problem that nature or quantum physics solves anyway. And then you can let it find the solution, and then you translate the solution back to your problem. And now it's very hard to find this translation still. We need very clever people in the future who find these translations, and they are not yet around for most of the problems. So if someone is a short-term investor, so for example, Kai, if you want to use your quantum computer within the next 5 years, I have to disappoint you, because it will take much longer to develop that, both the hardware and the software. We don't have enough quantum software engineers. But if you are willing to wait until you're completely grown up, maybe in 10 years or 15 years, then I think you can be hopeful that we will have such software. Andrei, you ask for investors. I would say you need to have a lot of patience. You should not expect the benefit within the next 2 or 3 or even 5 years. Quantum research is at a very early stage still, and until you can really have an application that is better than what a conventional computer can do, I think it still will take 10 years or so. And this is not only because of the hardware, it's really because we need these people who write the programs. It's great that Kai did Python programming, and maybe it's worth investing into the education of young, clever people to learn that. But,
May I ask then a question? For example, for protection of IP for patenting, a life of a patent is 20 years. Is there any point of patenting inventions today if the applicable timeline we're looking at 10 years? For example, in pharma, we can protect something today and we're going to benefit from it in 10 or 15 years. And the lifetime of this technology is going to still be profitable for the industry, even if it's going to be 5 or 10 years. For quantum, do you expect the same or something similar?
I think it depends on whether you can already maybe prove or the use a bit earlier. But I don't know how long then the period must be that you can use the product, but I think most things that you would patent today can not be used earlier than in 10 years. I don't know what that means now in terms of whether it's worth investing on that time scale. But
it depends what's going to be the market. If it's in 10 years, it's going to take over the market. If, let's say, all the logistics companies in 10 years will be able to take this technology and optimize all their software and programs, that's $1 billion, it's hundreds of billions of dollars market. Obviously, this kind of IP is going to be useful. But if it's just going to be something basic, then probably not. So
Yes.
what do you think the impact of this technology will be?
The potential impact is very large, but for any particular patent that you do now, it's of course, in a sense, hard to predict. But most problems we have today, like the one that Kai mentioned, the one you mentioned, and so on, are optimization problems. And of course, if you can only optimize things by a small amount, let's say, I mean, there are certain processes in chemistry where people are hopeful that we can make them more efficient. And they are used on such a large scale that even a small improvement would have an enormous benefit. There I could see that it would be worth having patents. So I think it's really a high risk thing, but with a potentially huge impact. I think if the problem that Kai mentioned can be solved, the flight routes will be shorter, and that will save a lot of money.
And maybe you could just describe really briefly how optimization would work on a quantum computer.
There is something, maybe I mentioned this technical term for those who want to look it up. There's something called the Grover algorithm. And this is a very useful algorithm because what it does is the following. So suppose you want to find out what is the best route for your airplane. And let's say you draw all these routes, and let's say there are 1 million possible routes, and you have to calculate the length of each of them. Now, a conventional computer really has to look at all these 1 million routes and just calculate the length, which is a lot of work. Now, a quantum computer only has to look at the square root many, which in this case will be only 1,000. Of course, a much smaller number than 1 million. We have many problems where there are maybe 10 to the 20 possibilities. That's 1 with 20 zeros. Do you play chess, for example? I don't know.
Yeah.
So there you can check all the possibilities. Like you can imagine if you have to decide on what to do. Now a computer, a conventional chess computer, has to go through all of them, and this will take forever. A quantum computer could just only look at 10 to the 10. So it reduces the number to a 1 with only 10 zeros, which is still a large number, but it's still a much smaller one than before. So there are these algorithms that allow us to test much fewer possibilities before we find the optimal solution. And that's one example of an optimization algorithm.
Very cool. Well, we're getting close to kind of the end of our episode. So maybe just 2 quick last questions.
Yeah, will there be quantum networks like we had optical networks for classical computers? Is there this kind of infrastructure is going to be built to even use them?
Yes, I mean, there's actually a really strong incentive now building this because we can also do much more secure cryptography. Kai, do you know what cryptography is? Have you heard about it?
No.
This is if I want to say, let's suppose I want to send now a message to Katia now, and I want to make sure you don't hear it. How can I do that? That's very difficult, you can imagine, because you will listen to our conversation. But now there are ways to do it so that you will not hear anything about it. You will hear some noise, but you cannot make sense of the message. And that's cryptography, to hide message. You can use quantum networks to build much more secure cryptographic schemes than we have today, because today's cryptographic schemes will actually be hacked using quantum computers. That's one of the drawbacks, that quantum computers will be able to break most of the methods that we are using to hide messages. In particular, the public key crypto systems that we use, for example, to authenticate when we do e-banking and so on. Now, with quantum networks, we can do that. And here, people are now working very intensively on building such networks. So the answer is yes, there will be these networks, and they will mostly be used for secure communication. And I think that's a much more immediate application. So that's on a time scale where it's maybe worth to invest. Now, although it's expensive, you need a completely new infrastructure. You need optical fibers until the end point, cannot do with conventional electric cables. And that's, of course, restricting the range of application at the moment.
Kai, any last thoughts on quantum for the first episode?
No, but maybe for a second one there will be.
Very good. For the second one, we'll have more thoughts.
I need to think of questions because I think I already ran out now. So see you in 1 million years until I get my question.
See you in 1 million years. All right. Well, thank you so much, Renato and Andrei.
Okay,
Thank you
it was a pleasure.
us.
Thanks for the good questions. You did a great job, although you run out of them, but I'm sure you will have many more next time.
Thank you.